250 million years ago, the Iberian Peninsula was located further west with respect to the European plate. During the Mesozoic, the Iberian block began to slide eastward along a large fault inherited from the Hercynian orogeny. This is the North Pyrenean Fault, the trace of which is visible in the Pyrenees region. This major geological structure marks the southern end of the Pyrenees Regional Natural Park. This North Pyrenean Fault is a real geological frontier between two continental entities that can be qualified as tectonic plates, the Eurasian Plate and the Iberian Plate. And in addition to being a geological border, this fault marks the geographical border between two natural regions of the Eastern Pyrenees, the Pyrenees and the Conflent, a border between two regional natural parks, Corbières Pyrenees and Pyrenees Catalans, without forgetting that it corresponds roughly to the historical border between the Kingdom of Aragon and the Kingdom of France from 1258 to 1659. Before going through this great fault, here is a small reminder of the geological context since 540 million years. During the Paleozoic era, several events occurred, including the colonization of the oceans by living organisms and the conquest of land. We look at plate tectonics is at the origin of the formation of several mountain chains, the Cadomian chain, which marks the end of the Precambrian times, the Caledonian chain in the north of Europe and especially the Hercynian or Variscan chain which structures Europe, part of Africa and North America. The major events that concern our subject are first situated around 300 million years ago with the formation of the Hercynian chain. It was during this very eventful period that the geological formations were transformed, deformed and major fractures cut through this basement, including the North Pyrenean Fault. During the Mesozoic, sedimentary basins were formed between the Iberian and the Eurasian blocks. At the end of the Mesozoic, these two blocks came closer together, lifting and deforming the accumulated sediments to form the Pyrenees from the Tertiary. Here is what this chain looks like nowadays. It stretches from the Mediterranean to the Atlantic. The North Pyrenean Fault marks the northern part of the chain. And in cross-section, the chain is a fan-like double-wedged range with a northward and southward overthrusts from the axial zone. And in the east of the Pyrenees, the geological formations are affected by numerous structures and remarkable deformations divided into several zones separated by important fractures. The core of the Pyrenees includes the axial zone, the backbone of the range, bordered to the north by the North Pyrenean Fault. It is essentially made up of deformed metamorphic Paleozoic terrains and magmatic bodies from the Hercynian cycle. North of the North Pyrenean Fault, the North Pyrenean zone comprises folded and faulted Mesozoic sedimentary rocks and continues northeastwards with the Corbières nappe, itself relayed by small chains to Provence. These complexes are bordered to the north by the North Pyrenean Front, which overlaps the Subpyrenean zone made up of weakly deformed sedimentary series. Finally, to the east lies the Roussillon Plain, which is a relatively recent collapse structure, graben, occurring during the Oligocene distension. We will now examine a portion of this North Pyrenean Fault over about 10 kilometers between Trevillach and Sournia. But first of all, let's see how the Pyrenees were formed and when it happened. At the beginning of the Cretaceous, Iberia was shifted westward with respect to Europe, leaving a marine space that connected the Atlantic and the Mesogean Sea, ancient Mediterranean. From the Aptian Albion, the Gulf of Gascony opens and the Iberian block drifts eastward in a rotational movement. In the Upper Cretaceous, the Iberian block moves northward and collides with the European block, lifting and deforming the previously deposited sediments. The compressional movement continues until the Eocene, which marks the climax of the uplift. At that time, Corsica and Sardinia, Corso-Sardinian block, were still attached to the European continent, and between the end of the Oligocene and the early Miocene this block started to rotate towards the east to its current position, opening up the Gulf of Lion. What are the main geological characteristics of the North Pyrenean Fault? The North Pyrenean Fault is an abnormal contact zone between Hercynian granitoids, 250 million years old, and Mesozoic limestones and marls, from 160 to 110 million years old. It borders the southern flank of the Boucheville Basin, an asymmetrical syncline with a bulge in its center and subvertical to inverted limbs. This north-south section through the Boucheville syncline shows sedimentary layers that have been overturned against the North Pyrenean Fault and the Millas granitic massif. The northern edge of the Boucheville syncline is also cut by the Trevillach Fault. This animation shows the Mesozoic sedimentary series lying on the basement at the end of the Cretaceous and subjected to the Pyrenean compression to reach the present configuration. The North Pyrenean Fault affects several geological formations at the contact of the fracture. These are essentially the metamorphic formations, marbles and hornfels on one side, and on the other side the granites of the Millas massif. The marbles have a banded structure marked by light and dark alternations, the latter being rich in organic matter. The marls, also metamorphic, have been transformed into a very hard fine-grained rock. The granites have a porphyroid facies comprising large crystals of potassium feldspars in a background of smaller minerals. One of the notable characteristics of the environment of this fault is this metamorphism particular to the Pyrenean chain. We can compare the two main types of metamorphism that differ by the pressure factor and the volume of affected rocks. First, the so-called regional metamorphism. It corresponds to a transformation of rocks under a medium-high pressure, 5 to 10 kilometers in depth, and a high temperature, 500 to 600 degrees Celsius. The rocks are transformed and acquire an orientation of its minerals, that is cleavage, schistosity or foliation. This metamorphism is found in the axial zone where it affects the formations subjected to the Hercynian orogeny. On the other hand, the Pyrenean metamorphism is of high temperature type, 500 degrees Celsius to 600 degrees Celsius, and low pressure, more or less 4 kbar. At this temperature, the limestone and marl rocks have undergone mineralogical transformations but little deformation due to pressure. These transformations are due to an increase in temperature. But what is the origin of this heat flow? This is due to a rise of the Earth's mantle at the level of the North Pyrenean Fault linked to a thinning of the Earth's crust. Under this fault, the temperature of the Earth's mantle is close to 1000 degrees Celsius, and this intense heat is transmitted to the sedimentary formations, which are thus metamorphosed but without undergoing significant pressure. When did this metamorphism occur? Radiometric dating on samples of metamorphic rocks date this metamorphism between 110 and 85 million years, thus Cretaceous. Zoom on the North Pyrenean Fault. The fault can be easily observed in various places between Trevillach and Sournia on 10 kilometers from east to west where it crosses the road several times. The flight over the area from the Auzines Pass to Sournia shows the Mesozoic limestone layers that mark out the fault. Its trace is easily identifiable at the foot of the limestone cliffs. The granitic formations of the Millas massif are in depression compared to the limestones. This is due to a more marked erosion of the granite subjected to an important fracturing against the fault and consequently to an important weathering. It should be noted that the limestone bars are not continuous and can sometimes disappear completely or be reduced to a few blocks packed in a sandy-clay mixture, e.g. near Sournia. This rapid variation is interpreted as resulting from a large-scale boudinage. Above Sournia, the panorama shows us successively, in the foreground, the Millas granites, in depression, in contact with the large limestone bars separated by the North Pyrenean Fault. The Boucheville Basin covered by a wooded relief, formed by the metamorphic marls, then the granitic massif of Agly, and in the background the syncline of Saint Paul de Fenouillet marked by large limestone cliffs. On this detailed geological map of the North Pyrenean Fault and its surroundings between Trevillach and Rambouillet, you can see the discontinuous marble outcrops, in blue, which mark out the North Pyrenean Fault, which is sometimes offset by transverse faults. Now, we are going to make some field observations along the fault following a road from the Auzines Pass to the Sournia quarry. For this, 7 easily accessible viewpoint areas have been selected. From Ile-sur-Tête, follow the D2 road to the Auzines Pass, where the panorama shows us in the distance the valley of the D6 river with village of Rambouillet, the Mesozoic limestone bars, the Millas granites in the foreground, as well as the metamorphosed Albian marls which form the reliefs. The D6 river and the Rapine stream follow the faulted contact between granite and limestone, its trace being located at the foot of the limestone reliefs. A zoom from the parking of the pass shows the differences of morphology between limestones devoid or almost of vegetation and the granites which emerge in the form of balls within a more abundant vegetation. We can also notice that the marls are also covered by a denser shrubby vegetation. A first field observation can be made in the abandoned quarry where the outcrops are in contact with the fault. The quarry is reached by a track 100 m before reaching the pass. The quarry face reveals a bedding of the marbles close to the vertical. The layers are made up of light and dark alternations. The light, white to pinkish layers rarely reach 1 meter in thickness. On observation, these marbles are affected by numerous deformations. Plastic deformations occurred in a ductile material in the form of microfolds. The plastic deformation is also expressed by a structure of boudinage which affects the white levels. The alternations of more or less competent levels are subjected to a layer parallel stretching that leads to these lenticular structures. This animation shows how stiffer levels in white are truncated by stretching along the bedding. Another very common type of deformation is the brittle deformation, which is superimposed on the microfolds and boudinages. These are isolated or networked microfaults that cut through the banded stratification. The brittle deformations are also expressed in the form of monogenic breccias, i.e. comprising angular debris all of the same carbonate nature. Finally, many large fault planes bear slickened sides, thus indicating the direction of movement, the sense being more difficult to determine. All these deformations occurred according to an order of appearance that can be determined thanks to superpositions of the structures. On this sample taken in the quarry we can observe several types of deformation as well as the order of their occurrence. Isoclinal microfolds were formed by ductile deformation in a plastic material. The tip of the hinge has been cut and offset by a small fault. The above white level is also offset. Several small fractures occurred when the marble had a brittle behavior. We leave the quarry in direction of Sournia following the D2 road. At the beginning of the DFCI track located 1 km before the Cantonal house we can observe the limestone cliff, called the Roc Blanc, which shows vertical and deformed layers. The flight over this limestone cliff shows overturned layers covering the more recent marls, and strongly inclined towards the south abutting against the Hercynian granitoids. Crushed limestones are in contact with the granites and mark the passage of the North Pyrenean Fault. We continue towards the intersection of the D2 and D619 roads, where the North Pyrenean Fault intersects these two roads. At the level of the Cantonal house and the Roman bridge, we can observe on the roadside outcrops of unweathered granite with large white minerals called porphyroblasts. These feldspars were formed early within a granitic magma. This animation shows how in a molten magma, the first crystals formed will grow slowly as long as the magma remains liquid. Then when the T degree decreases, the rest of the magma will crystallize more rapidly into smaller minerals, quartz, feldspars, mica. We continue the circuit towards the cave del Mean, where several observations can be made along the roadside. Here again the North Pyrenean Fault is visible on the edge of the D619 road, and an aerial view shows a large limestone bar cut by the North Pyrenean Fault on one side, the whole being offset by a transverse fault. The reading of the landscape is facilitated by the difference in color between the two lithologies, light gray marble on one side and light brown weathered granites on the other. The difference in vegetation also marks the passage from limestone to granite. The mean cave results from the karstic alteration in the marbles, and a few meters from cavities of karstic dissolution are marked by a filling of residual reddish decalcification clays whose color is due to the oxidation of clay minerals. The contact between limestone and granite can be seen a few meters from the cave. A fault plane partially masked by scree marks the passage of the fault. On the limestone outcrop, we can observe striations linked to the friction between the blocks located on both sides of the fault. These horizontal slickened sides indicate a horizontal movement but can be found elsewhere with a stronger inclination. This animation shows how we go from horizontal striations to inclined or even vertical striations. The limestones are crossed by a network of whitish veins. This is the filling of open fractures by calcite or quartz crystals that form from the edges of the vein towards the center. On the other side of the cave, the marls are very deformed, folded, fractured, and crosscut by numerous quartz calcite veins. The passage of a fault that offsets the North Pyrenean Fault is responsible for these intense deformations. This animation shows how from a simple open fracture, fluids with dissolved carbonates or silica circulated and lead the crystallization of calcite and or quartz. At 800 meters from the Mean cave, we find the North Pyrenean Fault cross-cutting the D619 road. Here the large limestone bars observed at the previous stop are reduced to 2 meters of a very deformed limestone, bordered on one side by granites also very deformed and on the other side by crushed marls. About 100 meters further, these marls are well developed in an old quarry showing massive bars of metamorphic marls. Now we move towards the last stage of our tour, the Sournia quarry. But first, let's make a stop at the village. An aerial view of the entrance to the village of Sournia shows different outcrops, which can be observed on the road sides. These outcrops are arranged in such a way that the limestones are interrupted and offset by about 100 meters by the passage of a transverse fault. An outcrop of crushed limestone is evidence of the passage of such a fault. To the west of Sournia, large slabs of overturned limestone have been cut by quarrying. In the topography, this feature forms chevrons in the streams that cut the layers. Here, the fault is hidden by the quarry debris but can be located at the foot of the limestone bars using the mapping. In the quarry, the limestones are much more massive, but locally we find the same microstructures, microfolds, boudinage, striated fault planes, etc. Beyond the quarry, towards the west, the North Pyrenean Fault continues, but it is less visible in the topography, due to the very reduced limestone levels being less visible. To summarize, we note that the North Pyrenean Fault is a major fault inherited from the Hercynian history, 300 million years ago, which played the role of a particularly active plate boundary. During the Cretaceous, it acted as a transform fault, allowing the slip of the Iberian block along the Eurasian plate. The ascent of the mantle beneath this fault caused a warming and the metamorphism of the calcareous and marly sediments. From the Upper Cretaceous, the northward movement of the Iberian block caused a collision between Eurasia and Iberia, leading to the formation of the Pyrenean chain, the climax of which occurred in the Eocene. The North Pyrenean Fault then had worked as a reverse fault under the effect of compression. From the Oligocene, the Gulf of Lion opened up as a result of the rotation of the Corso-Sardinian block, and a graben was formed at the present location of the Roussillon Plain in a context of extension. Nowadays, tectonic activity along and around the North Pyrenean Fault remains moderate, with evidence of local compression revealed by the focal mechanisms of recent earthquakes. However, we must not forget that the Pyrenean chain is still subject to the convergence of the Iberian and Eurasian plates.